Okay, this video is on the normal distributions. Normal distributions is probably one of the most important topics because normal distributions are used throughout the entire year in AP Statistics. So this is a pretty important video to make sure that we pay attention to. Alright, so first off, what is a normal distribution? Well, one really important type of density curve is called a normal curve. So we talked earlier about density curves, right? And one of the most famous density curves in the world is the normal curve. So let's make sure we understand the normal curve, but before we do that, I just want to make sure I remind you that density curves are models based on a mu, which is a mean, and a sigma, which is a standard deviation. They are not necessarily 100% realistic, but they're used to model data. So a normal curve is just a very specific model used for very specific types of data. So first off, a normal curve describes distributions that we call normal distributions. So in order to use a normal curve, you must be a normal distribution. So you see the word normal a lot. Now, a couple of characteristics of normal distributions. First off, all normal curves have the same shape, and that is symmetric, mound-shaped, bell-shaped, and single-peaked. So all of them have that same shape. There's not two normal curves that look completely different. They're all symmetric, they're all mound-shaped, and they are all bell-shaped. Bell-shaped is kind of that mound-shaped, just another word. And they're all single-peaked, which means that there's a single center in the middle that's kind of higher than everywhere else. Any specific normal curve is completely described by its mean and standard deviation. So every normal curve that's out there is defined by two numbers and two numbers only, and those two numbers are the mean and the standard deviation. And a couple more ideas here. Next, the mean is located at the center of the symmetric curve. Again, because the normal curve is symmetric, the mean is right smack dab in the middle. And if the mean is changed, then the entire curve is going to slide left or slide right. Obviously, as the mean changes, the whole curve will move with it. The standard deviation controls the spread of a normal curve. A larger standard deviation produces curves that are more spread out. A smaller standard deviation produces curves that are kind of more tight and compact. Now, understand that data that is quote-unquote normal will fit this shape. Not all data that looks sort of like this is necessarily normal. So if data is described as being normal, then it fits this shape. But just because you think the data looks like symmetric and mound shaped doesn't necessarily mean it's guaranteed to be normal. So it kind of only works one way there. Data that is normal fits everything I just went through. If data kind of looks like that, it might not necessarily mean it's normal 100%. So without further ado, here is what the normal curve looks like. All right, here's two examples, and notice that they both are mound-shaped and symmetric, single-peaked in the center. Now, for both of them, they have a mean that is right smack dab in the middle. So the mean is always right smack dab in the middle, mu and mu. Notice I'm not using X bar here. We don't use X bar here because X bar is realistic from real data. This is all model data, so we use the mu for the mean. Now, here's an example of one that's a little larger standard deviation where we are a little bit more spread out. And here's one with a smaller standard deviation where things are a little bit tightly and compact. Now, just like any other density curve, 100% of our data is underneath this curve. So when my standard deviation gets smaller, then the center is going to have to go higher, obviously, to still maintain the 100% of data in that curve. Now, a couple other important things is we've always said for a long time now that typical data is within one standard deviation of the mean. So if I'd go about the same distance this way, I get my value there. Now, one standard deviation, so one standard deviation goes right to about here. Now notice that this is an important part of the curve. This is where the curve turns from concave to convex. Now, if you've taken other class, you may know what that means. But basically, here's my curve, and it's going down the roller coaster, and here's where it kind of makes that switch to looping out. So here's concave is this part right here, and versus this is convex. So that's where the one standard deviation occurs where that change is made. So in this case, it's about right here. Again, it's where I change from this kind of curving out or curving in to curve, I guess this would be curving out to curving in, if that makes sense. So that is where one standard deviation occurs. And again, looking at the data, a lot of data, or the majority of data, does fall within that one standard deviation, just like we've been saying for quite a long time now. So that is what the normal curve looks like. Get used to drawing them. They're very easy to draw. All you got to do is draw your number line and try to make it as slim as mine, and then you make your nice bell-shaped curve. So hopefully you start to learn to make them real nice and neat. All right, why are these normal curves so darn important? Well, they're really important for a couple reasons. One, normal distributions are good descriptions for some distributions of real data. So they are great descriptions for real data. Now, not all data. I say that a lot of data looks normal, but there's also a lot of data that doesn't. But since so much data does look normal, it's why it becomes this pretty popular curve. For example, SAT scores are very, very normal, right? Meaning that most kids get some kind of average number. Very few kids score at this really high end, and very few kids score at this low end. That's the SAT scores. IQ fits this normal model. So again, draw a normal model. Most people have an average IQ. Very, very few people have an extremely large IQ, and very, very few people have a really low IQ. Most people kind of fall into this range, one standard deviation above to one standard deviation below. What else fits a normal curve in the real world is repeated measurements of the same object. For example, tennis balls, right? Let's just say that we have 1,000 tennis balls. Well, tennis balls are all very, very similar. They are pretty much the same thing. Now, if I measured the diameter of those tennis balls, some might be a teeny bit higher and some might be a teeny bit lower, but most tennis balls are going to fall really close to the average tennis ball. It's going to have a very small standard deviation because they're all pretty much the same. Now, every now and then you might get a very few that are a little bit bigger than they were supposed to be made. Some of them are very smaller than they were supposed to be made, but most should fit a nice normal model. So there's a lot of things in this real world that follow this normal model pattern. Now, what else are they good for? Why else are they so important? They are good approximations of many chance outcomes. So good approximations of chance outcomes. And obviously we're going to get more into this when we learn about probability. But what we're talking about here is that when something has a chance, let's talk about a coin, right? When you flip a coin, you could get heads, you could get tails. Now let's just say that I'm going to flip 10 coins, okay? When I flip 10 coins, I should have 5 heads and 5 tails, right? But sometimes you might have a little bit more heads and sometimes you might have a little bit less heads. So if I'm simply looking at how many heads there are when you toss 10 coins, and I toss 10 coins repeatedly, a lot of times, not just once, but a lot of times. Remember, most of the time, I should get that nice, perfect number of 5. When you toss 10 coins, you should get 5 heads. Now, sometimes you might get 6, 7, 8, 9. It would be really, really rare to be way out here where you get all 10 heads, and likewise, it would be really, really rare to have no heads. But most of the time, you should have somewhere between, 4 to 6 heads would be pretty typical. And again, that follows the normal model thinking that most of the time you should get something very, very similar to what you expect, 5 heads. You could get extremely high and extremely low, but the chances for that are extremely low. That's not going to happen in very many tosses of 10. And lastly, many statistical inference procedures based on normal curves. So when we learn about statistical inference is this idea, statistical inference is this idea of learning something from a sample and trying to make predictions about a population. In order to do this accurately, normal curves really help because normal curves are so famous and so used that a lot of data does fit normal curves. So if we want to try to predict what's going to happen in a sample or in a population, normal curves are kind of the way to go. So these are the 3 most important reasons why normal curves are so darn important. All right, so let's talk about a couple really important aspects of the normal curve, and one is something that we call the empirical rule. Now, some people call it the empirical rule, others call it the 68, 95, 99.7 rule. Kind of a weird name for a rule, but you'll understand what these 3 numbers mean. All right, so here's back to our vocabulary test scores that we learned about in our density curve video. And when we took this Iowa test, which is a test for vocabulary, the average score was 6.84 and the standard deviation is 1.55. Now we could build a normal curve with this. So right smack dab is going to go that mean of 6.84, and then we can go up 1 standard deviation, so I added 1.55, and then we can go up 2 standard deviations, so I added another 1.55, or we could go up 3 standard deviations. Now why didn't I go more? Because it would be very, very unlikely, that's why the line is so razor thin down here, to be higher than 3 standard deviations. Same thing with -1. I just subtracted 1 standard deviation, which is 1.55. Go down 2 standard deviations, so I subtract 2 1.55s, and then 3 standard deviations. Again, why do I not go to 4 or 5 or 6 standard deviations? Because the chances of being that low are extremely rare. Now, what this rule tells us, the empirical rule tells us that when we're looking at data that follows the normal curve, from -1, remember, that's that curve where it's going to make that turning point there, to +1. 68% of data falls in that range. So 68% of data falls within -1 and +1 standard deviations. So for a long time when we've been saying, hey, typically data falls within 1 standard deviation, that's kind of what we're talking about. Most data does fall in that range of -1 to +1 standard deviations. How much data? Well, approximately with this model, about 68% of data. And then from -2 to +2, inside that range is 95% of data. So 95% of data falls in that range. So in this particular vocabulary test, 95% of kids will score from -2 to +2. And the last number goes from -3 to +3 standard deviations. 99.7% of data will fall between those two values. So you could see that very little data falls outside of 3 standard deviations, and that's why we don't even draw +4 or -4 on the graph, because there's no need to. It's extremely rare to be outside of that value. So the empirical rule is the one that tells us that for a normal model, we have 68% of data in between -1 and 1, 95% of data in between -2 and 2 standard deviations, and 99.7% of data in between -3 and +3 standard deviations. Here's a nice chart that kind of makes this really, really simple to understand. First off, notice right smack dab in the middle is 0. 0 is considered the mean of our model. Why? Because remember, the mean is 0 standard deviations from itself. It is the mean. So that's why we have 0 there. And then we have +1 standard deviation, 2 standard deviation, 3 standard deviations, and that's what this is measuring on the bottom, -1, -2, -3. So we get this graph that shows us that 68%, 95%, 99.7%. So typically we could ask questions like, what's above 2 or what's outside of 2? Well, you got to have to walk through this, right? If there's 95% data in between -2 and +2, that means there's 5% of data left out, right? But because of symmetry, that 5% is split evenly. So when we look at this graph, we see that above +2, right? Anywhere above +2 is 2.5% of data. So this part up here, anything from 2 and above, is 2.5% of data. Same thing anywhere from -2 below is also 2.5% of data, because that's the 5% of data that got left out when the middle 95 was from -2 to +2. And that's why you could see that up here, right, in this area that would be above 3, this very, very small area, well, that would be, let's see here, that's only 0.3% of data that's left out. If you cut that in half, that's 0.015. So that's 0.3 cut in half, is 0.15%. So anyway, I messed that up. 0.15%. Again, that's well less than 1%. 0.15% of data is actually above 3. Same thing down here below. 0.15% is below -3 standard deviation. So you see why that percentage of data is just so rare. Very little data ever falls outside of that. So most data does fall within -2 to +2, and it's extremely rare to be much higher than that. And that's what the empirical rule tells us. All right, so now we have what's called the standard normal model. The standard normal model is a normal model based solely on z-scores. So remember, a standard normal model has a mean of 0 and a standard deviation of 1. That why when we draw a picture of this, and again, I'm sorry that I really struggle to draw in here, but anyway, we have 0 in the middle. We go +1, +2, +3, and this is how you would draw one. And again, this should be really, really low. Again, I'm sorry, my drawing skills aren't very good, but you get the idea here. So here's 0, here's 1, here's 2, here's 3. 3 should be way out there with very little above it. -1, -2, -3. No need to go to -4, +4, because it doesn't matter. Now, when we have these normal models, you can put any variable that fits a normal model on this graph. So this is kind of cool, right? This normal model is very useful because it's standardized. It's based on normal curves. So I could talk about, where does Susie's test score fall? Well, Susie had a kind of a low test score. She was, down here some real low. Or I could also say, well, what about an orange? That's a small orange. And I could say, oh, wow, that orange is actually the same place as Susie's score. So Susie and that orange, Susie and an orange are very different. But you could actually compare Susie and that orange if you say Susie's test score is just as low as that orange is in terms of how far it is from its mean. So these standard normal curves allow us to kind of put anything we want onto one of these curves as long as we base it on z-scores. Now, when we make normal models, we use an abbreviation for them. So we use a capital N for a normal model, and then in parentheses next to it we put the mean and the standard deviation. So this is telling us how that normal model is built. So for example, if I say here's a normal model 15, 2, that means that the normal model has a mean of 15, so that's your middle, and then it has a standard deviation of 2. So this would be 17, 19, 21, down to 13, 11, and 9. So that's how we can make a standard normal model based off of knowing this information. This is just a way that we abbreviate what kind of normal model we have. So hopefully you now have a little idea of a normal model, and let's take a look at some examples. Now, our calculator is set. It's beautifully set to help us with normal model. So I'm going to teach you about how it does that. So your calculator and the normal model. The calculator can help you find areas or proportions above, below, or in between data values. But those data values must be turned into z-scores first, because your calculator speaks one language and one language only. It's like the universal language of statistics, that is z-scores. So once again, let me come back down to here. Your calculator can actually find percentages of data that are above or below certain values. But in order for the calculator to give you a data, or a percentage of data that's a below, so let's say for example I'm right here, right? In order for me to give the calculator to give me the percentage of data below this line or above this line, I need to give the calculator my z-score. I need to have the z-score to do it. So let me teach you how to do this. So here's the first example. Here's a normal model, 15, 2.6. That means the mean is 15 and the standard deviation is 2.6. It says, what proportion is less than 12? Well, I can't answer this until I find the z-score for 12. So I'm going to find 12 minus 15 divided by 2.6. So on my calculator, I'm going to do 12 minus 15, hit enter, get -3. Right? That's -3, or you could just do that in your head if you want. And then you're going to go ahead and divide that by 2.6, and we get -1.15. Always 2 decimals, please. So this tells us that this point, this 12, right, is kind of a special value. It's definitely below the mean, and it's a little bit more, right, than typically. Typically, you could be within -1 standard deviations, but we're a little bit lower than that. So anyway, what percentage of data is less than this? Kind of like asking you what its percentile is, the percentage of data less than that. Well, since this is based on the normal model, I don't need all the data to answer this. I could use my calculator. So here's how the calculator to do this. First off, you hit second and then vars. This is to get to the distributions, D-I-S-T-R. This is distributions. And the normal distribution is the most famous one. So look at the very, very top of this list. We have normal PDF and normal CDF. Now, we will never, ever, ever, ever use normal PDF. We'll always use normal CDF in this class. It stands for cumulative, meaning it's a built-up area. So we always want to use that area, so normal CDF. So I'm going to grab normal CDF, and then I want to ask the calculator, based on z-scores, to find a percentage for me. So what I want to do is I want to find the percentage of data that's less than this z-score, which represents 12, right? This is the z-score that represents 12. I'm not going to type 12 into my calculator. And by the way, if you're using your calculator and when you hit normal CDF, it doesn't look like it does on my screen, turn your stat wizards off. So go to mode, go all the way down the bottom, and make sure your stat wizard's turned off. Okay, so anyway, that's how you get to look like mine. Now, what I want to do is I want to think about an interval, right? I want to think about this normal curve. And I'm going to just draw a really rough picture. But right here is 0, right? And somewhere down here is -1.15. And I want to find this area that is below that z-score. Now, to do that, I need to tell the calculator an interval. A starting point and an ending point. My starting point and my ending point. Now my ending point is negative 1.15. The starting point would be somewhere way down here. Now technically we have to understand that there's very little data below negative 3, but there might be a teeny bit of data. So we do want to start real low. So what we do is we start at negative 99. Now that is just like an exaggeration of an extremely low z-score. Now that is an unfathomable z-score, but we want to start way down on the left. It's kind of like negative infinity basically, but we don't have an infinity button on our calculator. So we're going to start way down at negative 99. So we're going to tell the calculator, find the percentage of data from negative 99, comma, to negative 1.15. So this is going to find us the percentage of data that is below negative 1.5. Essentially negative infinity, way low, up to negative 1.5. It's got to go in as an interval. And this tells us there's about 12.51% of data below 12. So 12.51% of data is below 12, whatever this data is. Again, I just made these numbers up. So whatever this data represents, there's about 12.51% of data below a score of 12. So the first thing is I needed to find 12 z-score, and then I need to understand how to give an interval on the calculator using normal CDF to calculate that value. All right, let's practice some more. So let's just say that the average high school student sleeps 6.5 hours of sleep per night, right? So this is hours of sleep. But it deviates. Some kids get more sleep, some kids get less sleep. It deviates by 0.8. So 6.5 is my mean, 0.8 is my standard deviation. So I could say something like, what percentage of kids get more than 7 hours of sleep? What percentage of kids get more than 7 hours of sleep? Well, first off, my calculator will not understand 7 hours, but it will understand a z-score. So I got to find the z-score for 7. I know it's above, but I just don't know how much it is. So I'm going to go ahead and calculate this. 7 minus 6.5. Hit enter, divide by 0.8. It's just a little bit above. It has a z-score of 0.625. That's not an extremely high z-score, but 7 hours is slightly above the mean, but it's not outside of what we'd say is typical. So anyway, now I want my calculator to find the proportion of people that are above that. So I'm going to just draw a little picture here. Here's 0, and somewhere right around here is a z-score of 0.625. Obviously, 0.625 is pretty close to 0. And I want to find the proportion above this. So I have to start my interval at that z-score. So I'm going to start at 0.625, and I'm going to end way down here at positive 99. Again, it's just like me going towards infinity. So I'm going to go ahead and pull up normal CDF again. I'm going to go from 0.625 and I'm going to go to 99. Now notice you always got to go left to right. So I'm going to look above, so 0.625 to 99, and this tells me there's about 26.60% of data. So about 26.60% of kids will get more than 7 hours of sleep. Again, all I did was I calculated z-score, and then I went ahead and use the normal CDF. So what about between 7 and 8? Well, we already know that 7 is a z-score of 0.625. Now we just got to find the z-score for 8. So that would be 8 minus 6.5 divided by 0.8. So 8 minus 6.5. Hit enter, divide by 8 next, I get 1.875. So the z-score here is 1.875. That is a pretty high. So getting 8 hours of sleep is very unusual for a high school student. So anyway, now since I want to look in between those two z-scores, I'm just going to go ahead and grab a normal CDF. Make sure you don't ever grab PDF CDF, and I'm going to do 0.625, comma, 1. What was it again? I got to look. 1.875. So 1.875. Close that parenthesis, and this is going to tell you the proportion of data in between. So about 23.56% of kids. 23.56% of kids get between 7 and 8 hours of sleep. Again, this is a model. It's not guaranteed to happen, but it's just a model. Okay, what about below 5 hours? Well, once again, I got to start off by finding the z-score for 5 hours. So 5 minus 6.5 divided by 0.8. And 5 minus 6.5, hit enter first, divided by 0.8. I get a z-score that is negative 1.875. So notice that over here I got 8 was positives. This means that 8 is just as unusual as 5 is, but on the other end, obviously. So again, I want to find the percentage below this. So when I go below this, somewhere down here is negative 1.875, and I want to find below it. So again, starting point, ending point. So I'm going to start way down at like negative infinity, but for me that's going to be negative 99 because I don't really have a negative infinity button. So negative 99, comma, negative 1.875. And this is going to tell me that there's a very low percent, about 3.04%. So about 3.04% of high schoolers get below 5 hours of sleep. That's good because you definitely don't want to get too few hours of sleep. All right. Henry sleeps 7.5 hours. What percentile is he? Again, what percentile is, that's the percent below. So I just got to find Henry's z-score, and then I could find the percent below Henry by using my calculator. So it's a very similar question to all of these. I just got to use my calculator to get it. So 7.5 minus 6.5 divided by 0.8, so that's a z-score of 1.25. Well, it's kind of a little bit high, so let's figure out where that puts Henry at. So again, I'm going to look below. So when I start below, I'm going to start at negative 99, way down there, negative infinity, and I'm going to go up to his z-score. Always got to work left to right on the normal model using normal CDF, and I get about 89.43%. So he would, usually percentiles we just rounded to, so the 89th percentile. So Henry does get a good amount of sleep. In fact, only about 11% of kids get more sleep than Henry. So pretty simple there. Hopefully that all makes sense. Okay, now we could also use z-scores in reverse. This is pretty important as well. So for example, instead of me asking you for the percentage, I'm going to give you the percentage. So what z-score has 20% below it? So I need to figure out what z-score has 20% below it. My calculator will come in handy for this as well. Once again, I'm going to go to second vars. This time I'm going to go down to Invert Norm, INV Norm. Invert Norm will tell you the z-score that has a percentage below it. So you have to just simply input the percent below, and it will tell you the z-score that has that percent below it. So I'm just going to type in 0.20 to represent 20%, and this tells me that a z-score of negative 0.84 has 20% below it. So a z-score of negative 0.84 is connected with 20% below it. So that's how invert norm works. You type in the percent below. And then if I could say, well, how many hours of sleep is this? Well, I could plug this into my formula where I know the mean, I know the standard deviation, and I now know the z-score that has 20% below it, and I could back solve. So I could take negative 0.84, I could times it by 0.8, and then I could add over the 6.5, and if you get 5.83 hours of sleep, then 20% of people have less sleep than you. So again, you could solve for that. Okay, how about this one? What z-score has 5% above it? Now, we've got to be careful here because it says above. Invert norm only accepts percents below. So you have to understand that if I'm talking about the upper 5%, that is the same thing as talking about the lower 95%. It's the same value. The same value has 5% above it as has 95% below it. So in this case, I'm going to put in, excuse me, I did that completely opposite of what I was meaning to tell you to. I'm going to put in 0.95. Again, invert norm must take the percent below. So the percent below, 95% below, is the same thing as 5% above. So 1.64 would be the z-score that has 5% above it. It also is the same z-score as 95% below it. Once again, if I want to solve for this, I do x minus 6.5, all divided by 0.8. So 1.64 times it by that standard deviation, add over the mean of 6.5, and if you get 7.8 hours of sleep, then you are in the top 5%, right? Only 95% of kids get less sleep than you, only 5% get more than you. You get a lot of sleep, basically. Here's one more question, just worded a little bit differently. 45% of all data is above what z-score? Once again, it says above. Well, I have to understand that if I'm talking about a value that is 45% above it, I might as well be talking about a value that is 55% below it. It's the same value. Why is this important? Because invert norm only accepts the percent below. So you need to kind of convert that on your own, that I'm talking about 45% above is the same thing as 55% below. So that gives me a z-score of 0.1256. So a z-score of let's see here, 0.13 basically would be my z-score. Now, once again, Hopefully that all makes a lot of sense to you. Be very, very careful with the whole idea of 45% above means 55% below. This is pretty close to 0. Why is this pretty close to 0? Because guess what value has 55% has 50% above it and 50% below it? 0. A z-score of 0, the mean, right, has 50% above it, 50% below it. So that's a quick, or maybe not so quick, but a nice video on using the normal model.